Now is about higher order differential equation. So the method of undetermined coefficients has two inherent weaknesses that limit its wider application to linear equations. So first is that the differential equation must have constant coefficients. And second, the input function g of x must be of a specific type or form. So we introduce another method of solving differential equations. We have variation of parameters. So the variation of parameters is the method of determining a particular solution y of p or yp of a non-homogeneous linear differential equation that has no restrictions. Now let's take a look back at this linear first order differential equation. So we have this form. Its solution is equivalent to this equation, where our first term is called the characteristic equation or yc, and our second term called the particular solution yp. So now looking at the particular solution, our yp just equivalent to yc times some function. So let's label that function as u of x. So suppose that we have y1 as a known solution. So where our dy dx plus p of x y1 equal to 0. So it is a solution to the associated homogeneous equation. So our particular solution just equivalent to some function. Let's label this as u1 of x times the characteristic equation y1 of x. Now if you substitute this particular solution to this differential equation, we have u1 y1 plus p of x u1 y1 equal to f of x. Now using the product rule, we have, so we can write this equation as y1 du1 dx plus, we can factor out u1, so u1 times dy1 dx plus p of x y1 equals to f of x. Now since y1 is an equation to the non-homogeneous differential equation, which is this one, so meaning this term right here is equivalent to 0. So how we are left with y1 du1 dx equal to f of x. Now finding u1 is just equivalent to integral of f of x over y1 of x dx. So our yp is equivalent to y1 times the integral of f of x over y1 of x dx. We're looking at this particular solution right here, just identical or just equivalent. So our ux is just equivalent to this. Now for a linear second order differential equation, so if we have this form, a complementary solution of yc is equal to c1 y1 plus c2 y2. So our particular solution, replacing c1 and c2, we have q1 y1 plus q2 y2. Now getting the first and second derivative of yp, so substituting that equation to this differential equation, just like with what we did before with the first order DE, we will arrive with the equations y1 q1 prime plus y2 q2 prime equal to 0, and then we have y1 prime q1 prime plus q2 prime y2 prime q2 prime equal to f of x. Now this equation, equations 1 and 2, can be expressed in terms of determinants. So y1 prime is just equivalent to w1 over w, and our y2 prime is just equivalent to w2 over w, where w is called the Wronskian of y1 and y2. So we have w is just equivalent to the determinant of y1, y2, we have y1 prime, y2 prime, and our w1 is equivalent to 0 f of x, y2, y2 prime, and our w2 is just equivalent to y1, y1 prime, we have 0 of x. So using these determinants, our y1 u1 prime is just equivalent to negative y2 f of x over w, and our u2 prime equivalent to y1 f of x over w. Now, solving for u1 and u2, just need to integrate these functions. So for example, find the general solution using variation of parameters. Find the general solution of this differential equation. So this equation has an auxiliary equation equivalent to m squared minus 4m plus 4 equal to 0. Or we have m minus 2 squared equal to 0. So our elementary solution equivalent to c1 e to the 2x plus c2 x e to the 2x. We have this our y1, and this is our y2. So our particular solution should be q1 e to the 2x u2 x e to the 2x. So our w is equivalent to, we have our y1 e to the 2x and our y2 x e to 2x. Now for the second row, need to get the first derivatives of y1 and y2. So first derivative of y1 is equivalent to 2e to the 2x. And for y2, using the product rule, we have 2x e to the 2x plus e to the 2x. Now getting the determinant of this matrix, we have e to the 2x times 2x e 2x plus e to the 2x minus x e to the 2x times 2e 2x. This is equivalent to e to the 4x. Now for w1, we have 0 and our f of x is this equation. X plus 1 e to the 2x. We have x e to the 2x 2x e to the 2x plus e to the 2x. Now getting the determinant of this equation, we have negative x plus 1 x e 4x. Now for w2, equivalent to e to the 2x 2e 2x. We have 0 x plus 1 e to the 2x. Getting the determinant of this matrix, we have x plus 1 e to the 4x. So our u1 prime equivalent to w1 over w. So we have negative x squared minus x. Then our u2 prime is equivalent to w2 over w is equal to x plus 1. Now integrating the two equations, u1 prime and u2 prime, we have our u1 is equivalent to integral of this equation as negative 1/3 x cubed minus 1/2 x squared. Then for u2 equivalent to 1/2 x squared plus x. So our yp is equivalent to this equation. We have negative 1/3 x cubed minus 1/2 x squared times e to the 2x plus 1/2 x squared plus x times xe to the 2x. Evaluating this equation, we have 1 over 6 x squared, x cubed e to the 2x plus 1/2 x squared e 2x. So our general solution is equivalent to the complementary solution plus the particular solution. So we have c1 e to the 2x plus c2 e 2x plus 1 over 6 x cubed e to the 2x plus 1 half x squared